In the late 1980s, databases evolved so that an application, called a client, on one machine could run against a database, called a server, on another machine. At first, this client, or server database architecture was only used on mini and mainframe computers. Between 1987 and 1988, vendors like Oracle Kohler and Optifus moved the client function and then the database server down to microcomputers and local area networks LANs. Today, the client or server concept has evolved to cover a range of approaches to distributing the processing of an application in a variety of ways between different machines. On any LAN, there will always be at least two entities. The client machine, which is used to make requests of the database, and the server machine, which stores the database and processes received requests. In general, the client or server architecture involves multiple computers connected in a network. Some of the computers, clients process application programs, and some computers, servers perform database processing. This approach is known as the two-tier model of client or server computing. As it is made up of the two types of component, clients and servers. It is also possible that a machine that acts as a server to some clients may itself act as a client to another server. This arrangement also falls under the two-tier model, as it still only comprises the two types of machine within the network. Simple client. As a client needs just a browser to run a web-based database application, the potential complications are minimized. Common interface across applications. Again, because there is no need for specialized software, users have the benefit of using a browser for possibly different applications. Limited GUI, graphical user interface. This is one area in which web-based database applications may fall short. Highly customized application interfaces and highly interactive clients may not translate well as web applications. This is because of the HTML limitations. At the moment, HTML forms do not offer an extensive feature set. Although JavaScript language can extend the functionality of HTML-based applications, it is too complex, adds to downloading time, and degrades performance. Integrate with other applications. Because of the benefit of being platform independent, different applications that adhere to the HTML standard can be integrated without many difficulties. The client. This is the front end of the client or server system. It handles all aspects of the user interface. It is the front end of the system since the client presents the system to the user. It provides PC-based application development tools used to enter, display, query, and manipulate data on the central server, and to build applications. The client operating system is usually Windows, OS/2, or Unix. The server. Servers perform functions such as database integrity checking, data dictionary maintenance, and provide concurrent access control. Moreover, it performs recovery and optimizes query processing. The server controls access to the data by enforcing locking rules to ensure data integrity during transactions. The server can be a PC, mini, or mainframe computer and usually employs a multitasking operating system such as OS/2, Unix, or MVS. Multimedia support. HTML already provides easy-to-use constructs to present and manipulate multimedia contents. Non-persistent connection to database. Persistent database connections are highly efficient data channels between a client and the DBMS, and therefore are ideal for database applications. However, web-based applications do not have this benefit. Apart from the above differences, there are some other important concerns for web-based applications. Reliability of the Internet. Security. The following diagram illustrates how a user interacts with a client system, which transmits queries to the database server. The server processes the queries and returns the results of the query, or a code indicating failure of the query for some reason. Typically, in a client or server environment, the user will interact with the client machine through a series of menus, forms, and other interface components. Supposing the user completes a form to issue a query against a customer database. This query may be transformed into an SQL select statement by code running on the client machine. The client will then transmit the SQL query over the network to the server. The server receives the command, verifies the syntax, checks the existence and availability of the referenced objects, verifies that the user has select privileges, and finally executes the query. The resulting data is formatted and sent to the application, along with return codes used to identify whether the query was successful, or if not, which error occurred. On receipt of the data, the client might carry out further formatting. For example, creating a graph of the data before displaying it to the user. Components of a web database application. Web database applications may be created using various approaches. However, there are a number of components that will form essential building blocks for such applications. In other words, a web database application should comprise the following 4 layers, that is, components. Browser layer, application logic layer, database connection layer, database layer, browser layer. The browser is the client of a web database application, and it has 2 major functions. First, it handles the layout and display of HTML documents. Second, it executes the client-side extension functionality such as Java, JavaScript, and ActiveX, a method to extend a browser's capabilities. Users do not have to retain copies of corporate data on their own PCs, which would become quickly out of date. They can be assured that they are always working with the current data, which is stored on the server machine. Processing can be carried out on the machine most appropriate to the task. Data-intensive processes can be carried out on the server, whereas data entry validation and presentation logic can be executed on the client machine. This reduces unnecessary network traffic and improves overall performance. It also gives the possibility of optimizing the hardware on each machine to the particular tasks required of that machine. Scalability. If the number of users of an application grows, extra client machines can be added without significant changes to the server. The 2 most popular browsers at the present are Netscape Navigator, Netscape, for short, and Microsoft Internet Explorer, IE. They have their own advantages and disadvantages with respect to web database applications. Both browsers support Java, JavaScript, and IE also supports ActiveX. Netscape is supported on numerous platforms, whereas IE runs only on Microsoft systems, example, Windows 98 and NT. IE offers compatibility with other Microsoft products and can easily be integrated with existing tools such as Word, Excel, and PowerPoint. The drawback is that IE heavily dependent on the Windows platforms and other Microsoft proprietary systems. ActiveX is designed to extend the functionality of IE and works only on Windows platforms and Macintosh System 7+. Operating database systems over a LAN, or wide area network, WAN, brings extra complexities of developing and maintaining the network. The interfaces between the programs running on the client and server machines must be well understood. This usually becomes increasingly complex when the applications and/or DBMS software come from different vendors. Security is a major consideration, as preventative measures must be in place to protect data theft or corruption on the client and server machines and during transmission over the network. Both Netscape and IE are graphical browsers. There is another browser, called Lynx, which is a text-based one. As loading graphics over the internet can be a slow and time-consuming process, database performance may be affected. If an application requires a speedy client and does not need to display graphics, then the use of Lynx may be considered. All browsers implement the HTML standard. The discussion of HTML is beyond this unit, but you need to know that it is a language used to format data or documents to be displayed on the web. Browsers are also responsible for providing forms for the collection of user input, packaging the input, and sending it to the appropriate server for processing. For example, input can include registration for site access, guestbooks, and requests for information. HTML, Java, JavaScript, or ActiveX, for IE may be used to implement forms. Business logic implemented as stored procedures. The main mechanism for placing business logic on a server is known as stored procedures. Stored procedures are collections of code that usually include SQL for accessing the database. Stored procedures are invoked from client programs and use parameters to pass data between the procedure and invoking program. If we choose to place all the business logic in stored procedures on the server, we reduce network traffic, as intermediate SQL results do not have to be returned to client machines. Stored procedures are compiled, in contrast with uncompiled SQL sent from the client. A further performance gain is that stored procedures are usually cached. Therefore, subsequent calls to them do not require additional disk access. Application logic layer. The application logic layer is the part of a web database application with which a developer will spend the most time. It is responsible for collecting data for a query, example, a SQL statement, preparing and sending the query to the database via the database connection layer, retrieving the results from the connection layer, formatting the data for display. Most of the application's business rules and functionality will reside in this layer. The browser client displays data as well as forms for user input. The application logic generates HTML that the browser renders. Also, it receives, processes, and stores user input that the browser sends. Two-tier client or server architectures in which a significant amount of application logic resides on client machines suffer from the following further disadvantages. Upgrades and bug fixes must be made on every client machine. This problem is compounded by the fact that the client machines may vary in type and configuration. The procedural languages used commonly to implement stored procedures are not portable between machines. Therefore, if we have servers of different type, for example, Oracle and Sybase, the stored procedures will have to be coded differently on the different server machines. In addition, the programming environments for these languages do not provide comprehensive language support as is found in normal programming languages such as C++ or Java, and the testing or debugging facilities are limited. Database connection layer. This is the component which actually links a database to the web server. Because manual web database programming can be a daunting task, many current web database building tools offer database connectivity solutions, and they are used to simplify the connection process. The database connection layer provides a link between the application logic layer and the DBMS. Connection solutions come in many forms, such as DBMS Net Protocols, API Application Programming Interface, or class libraries, and programs that are themselves database clients. The following diagram illustrates how a user interacts with a client system, which deals with the validation of user input and the presentation of query results. The client system communicates with a middle-tier system, the application server, which formulates queries from the validated input data and sends queries to the database server. The database server processes the queries and sends to the application server the results of the query, or a code indicating failure of the query for some reason. The application server then processes these results, or code, and sends data to the client system to be formatted and presented to the user. The three-tier architecture introduces an application server, which is a computer that fits in the middle between the clients and server. With this configuration, the client machines are freed up to focus on the validation of data entered by users and the formatting and presentation of results. The server is also free to concentrate on data-intensive operations, that is, the retrieval and update of data, query optimization, processing of declarative integrity constraints, and database triggers, etc. The new middle tier is dedicated to the efficient execution of the application logic. The application server can perform transaction management, and if required ensure distributed database integrity. It centralizes the application logic for easier administration and change. The three-tier model of client or server computing is best suited to larger installations. This is true because smaller installations simply do not have the volume of transactions to warrant an intermediate machine dedicated to application logic. The distribution of data by an organization throughout its various sites and departments allows data to be stored where it was generated, or indeed is most used, while still being easily accessible from elsewhere. The general structure of a distributed system is shown below in the diagram. In effect, each separate site in the example is really a database system site in its own right, each location having its own databases, as well as its own DBMS and transaction management software. It is commonly assumed when discussion arises concerning distributed database systems that the many databases involved are widely spread from each other in geographical terms. Importantly, it should be made clear that geographical distances will have little or no effect upon the overall operation of the distributed system. The same technical problems arise whether the databases are simply logically separated, as they would if separated by a great distance. Fragmentation independence. A fragment can be any arbitrary subrelation that is derivable from the original relation via restriction, horizontal fragmentation and projection, vertical fragmentation operations. Fragmentation independence, also known as fragmentation transparency, therefore, allows users to behave, at least from a logical standpoint, as if the data were not fragmented at all. This implies that users will be presented with a view of the data in which the fragments are logically combined together by suitable joins and unions. It is the responsibility of the system optimizer to determine which fragment needs to be physically accessed in order to satisfy any given user request. Replication independence. A system supports data replication if a given stored relation, or, more generally, a given fragment, can be represented by many distinct copies, or replicas, stored at many distinct sites. Replication is desirable for at least two reasons. First, it can mean better performance. Applications can operate on local copies instead of having to communicate with remote sites. Second, it can also mean better availability. A given replicated object, fragment, or whole relation remains available for processing so long as at least one copy remains available, at least for retrieval purposes. Fragmentation problem. Both data replication and fragmentation have their related problems in implementation. However, distributed non-replicated data only has problems when the relations are fragmented. The problem of supporting operations, such as updating on fragmented relations, has certain points in common with the problem of supporting operations on join and union views. It follows that updating a given tuple might cause that tuple to migrate from one fragment to another if the updated tuple no longer satisfies the relation predicate for the fragment it previously belonged to. Replication also has its associated problems. The major disadvantage of replication is that, when a given replicated object is updated, all copies of that object must be updated, the update propagation problem. Therefore, in addition to transaction, system, and media failures that can occur in a centralized DBMS, a distributed database system, DDBMS must also deal with communication failures. Communications failures can result in a site holding a copy of the object being unavailable at the time of the update. The 2PC protocol works in the following way. Commit or rollback is handled by a system component called the coordinator, whose task it is to guarantee that all resource managers commit or roll back the updates they are responsible for in unison, and furthermore, to provide that guarantee even if the system fails in the middle of the process. Assume that the transaction has completed its database processing successfully, so that the system-wide operation it issues is commit, not rollback. On receiving the commit request, the coordinator goes through the following two-phase process. First, the coordinator instructs all resource managers to get ready either to commit or roll back the current transaction. In practice, this means that each participant in the process must force write all log entries for local resources used by the transaction out to its own physical log. Assuming the force write is successful, the resource manager now replies OK to the coordinator, otherwise, it replies not OK. When the coordinator has received replies from all participants, it force writes an entry to its own physical log, recording its decision regarding the transaction. If all replies were OK, that decision is commit. If any replies were not OK, the decision is rollback. Either way, the coordinator then informs each participant of its decision, and each participant must then commit or roll back the transaction locally as instructed. If the system or network fails at some point during the overall process, the restart procedure will look for the decision record in the coordinator's log. If it finds it, then the 2PC process can pick up where it left off. If it does not find it, then it assumes that the decision was rolled back, and again the process can complete appropriately. However, in a distributed system, a failure on the part of the coordinator might keep some participants waiting for the coordinator's decision. Therefore, as long as the participant is waiting, any updates made by the transaction via that participant are kept locked. For the replica control protocol that enforces one-copy serializability is known as read once or write all ROWA protocol. ROWA protocol is simple, but it requires that all copies of a logical data item be updated before the transaction can terminate. Failure of one site may block a transaction, reducing database availability. A number of alternative algorithms have been proposed that reduce the requirement that all copies of a logical data item be updated before the transaction can terminate. They relax ROWA by mapping each write to only a subset of the physical copies. One well-known approach is quorum-based voting, where copies are assigned votes, and read and write operations have to collect votes and achieve a quorum to read or write data. Three-phase commit is a non-blocking protocol which prevents the 2PC blocking problem from occurring by removing the uncertainty for participants after their votes have been placed. This is done through the inclusion of a pre-commit phase that relays information to participants advising them that a commit will occur in the near future. Eager replication update strategies, as identified above, are synchronous in the sense that they require the atomic updating of some number of copies. Lazy group replication and lazy master replication both operate asynchronously. If the users of distributed database systems are willing to pay the price of some inconsistency in exchange for the freedom to do asynchronous updates, they will insist that the degree of inconsistency be bounded precisely and that the system guarantees convergence to standard notions of correctness. Without such properties, the system in effect becomes partitioned as the replicas diverge more and more from one another. Lazy group replication, however, allows any node to update any local data. When the transaction commits, a transaction is sent to every other node to apply the root transaction's updates to the replicas at the destination node. It is possible for two nodes to update the same object and race each other to install their updates at other nodes. The replication mechanism must detect this and reconcile the two transactions so that their updates are not lost. Timestamps are commonly used to detect and reconcile lazy group transactional updates. Each object carries the timestamp of its most recent update. Each replica update carries the new value and is tagged with the old object timestamp. Each node detects incoming replica updates that would overwrite earlier committed updates. The node tests if the local replica's timestamp and the update's old timestamp are equal. If so, the update is safe. The local replica's timestamp advances to the new transaction's timestamp, and the object value is updated. If the current timestamp of the local replica does not match the old timestamp seen by the root transaction, then the update may be dangerous. In such cases, the node rejects the incoming transaction and submits it for reconciliation. The reconciliation process is then responsible for applying all waiting update transactions in their correct time sequence. Transactions that would wait in an eager replication system face reconciliation in a lazy group replication system. Waits are much more frequent than deadlocks because it takes 2 waits to make a deadlock. Another alternative to eager replication is lazy master replication. This replication method assigns an owner to each object. The owner stores the object's correct value. Updates are first done by the owner and then propagated to other replicas. When a transaction wants to update an object, it sends a remote procedure call, RPC, to the node owning the object. To achieve serializability, a read action should send read lock RPCs to the masters of any objects it reads. Therefore, the node originating the transaction broadcasts the replica updates to all the slave replicas after the master transaction commits. The originating node sends one slave transaction to each slave node. Slave updates are timestamped to assure that all the replicas converge to the same final state. If the record timestamp is newer than a replica update timestamp, the update is stale and can be ignored. Alternatively, each master node sends replica updates to slaves in sequential commit order. Extended CGI. An improved version of CGI, called Fast CGI, has been developed by a company named Open Market. Fast CGI has the following features. Language independence. Same as CGI, Fast CGI is a protocol and not dependent on any specific language. Open standard. Like CGI, Fast CGI is positioned as an open standard. It can be implemented by anyone. Independence from the web server architecture. A Fast CGI application needs not be modified when an existing web server architecture changes. Distributed computing. Fast CGI allows the web application to be run on a different machine from the web server. Multiple, extensible roles. Fast CGI can provide multiple roles such as a filter role and an authorizer role. Memory sharing. With Fast CGI, different instances of the same application can access the same file from the same section of memory without duplication. Allocating processes. Fast CGI applications do not require the web server to start a new process for each application instance. Fast CGI seems to be a complete solution for web database programming, as it includes the best features of CGI and server APIs. HTTP server APIs and server modules. HTTP server, web server APIs, and modules are the server equivalent of browser extensions. The central theme of web database sites created with HTTP server APIs or modules is that the database access programs coexist with the server. They share the address space and runtime process of the server. Server vendor modules. Server modules are just prefabricated applications written in some server APIs. Developers can often purchase commercial modules to aid or replace the development of an application feature. Sometimes, the functionality required in a web database application can be found as an existing server module. Let us now look at the advantages and important issues of server APIs and modules. Having database access programs coexist with the HTTP server improves web database access by improving speed, resource sharing, and the range of functionality. Advantages: speed. Server API programs run as dynamically loaded libraries or modules. Resource sharing. Unlike a CGI program, a server API program shares address space with other instances of itself and with the HTTP server. Range of functionality. CGI programs have access to a web transaction only at certain limited points. Important issues. Server architecture dependence. Server APIs are closely tied to the server they work with. Platform dependence. Server APIs and modules are also dependent on computing platforms. Programming language. Both Netscape servers and Microsoft Web servers can be extended using a variety of programming languages and facilities. Connecting to the database. Database connection layer is built for the underlying database. Database connectivity solutions include the use of native database APIs. Native database APIs are dependent on the database they support. Database-independent APIs. The most popular standard database-independent API was pioneered by Microsoft. It is called ODBC, Open Database Connectivity, and is supported by all of the most popular databases such as Microsoft Access and Oracle. Template-driven database access packages. Template-driven database connectivity packages are offered by database vendors. Template-driven packages are very product-dependent. Third-party class libraries. Simplify web database application programming. Database API libraries. Database API libraries are at the core of every web database application and gateway. Database API libraries are collections of functions or object classes that provide source code access to databases. GUI application builders. Visual web database building tools offer an interesting development environment for creating web database applications. For developers accustomed to point-and-click application programming, these tools help speed the development process. For instance, Visual Basic or Microsoft Access developers should find such a tool intuitive and easy to use. GUI, graphical user interface, allowing developers to build a web database application with a series of mouse clicks and some textual input. These tools also offer application management so that a developer no longer needs to juggle multiple HTML documents and CGI, NSAPI, or ISAPI programs manually. Managing state and persistence in web applications. State is an abstract concept of being, which can be explained by a set of rules, facts, or truisms. A state in a database application includes a set of variables or other means to record who the user or client is, what tasks he or she has been doing, at what position he or she is at a particular instance in time, and many other useful pieces of information about a database session. Persistence is the capability of remembering a state and tracking state changes across different applications or different periods of time within an instance of an application or multiple instances. HTTP is connectionless, which means that once an HTTP request is sent and a response is received, the connection to the server is closed. If a connection were to be kept open between client and server, the server could at any time query the client for state information, and vice versa. URL, query string. Two basic methods offered by CGI to pass information between client and server are get method and post method. These methods can collect information for the server via a set of environment variables. By using this method together with the environment variable, query string, the server is able to find out the user's identity at login time and keep track of it thereafter. Query string works as follows. A registration or login page is delivered to the user. The user types in her username and password, and then submits the page. The username and password pair are sent to a server-side CGI program, which extracts the values from the query string environment variable. The values are checked by the server to determine whether or not the user is authenticated. If he or she is authenticated, the authenticated state is reflected in a randomly generated session ID, SID, which is stored in a database along with other necessary data to describe the state of the user session. The SID can then be stored in all URLs within HTML documents returned by the server to the client, and therefore tracking the identity of the user throughout the session. HTTP cookies. HTTP cookie is a technique that helps maintain state in web applications. A cookie is in fact a small text file containing name of the cookie, domains for which the cookie is valid, expiration time in GMT, application-specific data such as user information, etc. Cookies are sent by the server to the browser and saved to the client's disk. Whenever necessary, the server can request a desired cookie from the client. The client browser will check whether it has it. If it does, the browser will send the information stored in the cookie to the server. Important considerations. Managing state on the client. An application can maintain all of its state on the client side with any of the methods discussed in the previous section. Benefits of the client-side maintenance. An attraction of maintaining state on the client is simplicity. It is easier to keep all the data in one place, and by doing it on the client, it eliminates the need for server database programming and maintenance. Security issues in web database applications. Security risks exist in many areas of a web database application. This is because the very foundations of the Internet and web, TCP, or IP, and HTTP, are very weak with respect to securities. Security issues in web database applications include the following. Data transmission, communication between the client and the server is not accessible to anyone else, except the sender and intended receiver, privacy. Data cannot be changed during transmission integrity. The receiver can be sure that the data is from the authenticated sender, authenticity. The sender can be sure the receiver is the genuinely intended one, non-fabrication. The sender cannot deny he or she sent it, non-repudiation. The request from the client should not ask the server to perform illegal or unauthorized actions. The data transmitted to the client machine from the server must not be allowed to contain executables that will perform malicious actions. Proxy servers. A proxy server is a system that resides between a web browser and a web server. It intercepts all requests to the web server to determine if it can fulfill the requests itself. If not, it forwards the request to the web server. Firewalls. A firewall is a system designed to prevent unauthorized access to or from a private network, intranet. It can be implemented in either hardware, software, or both. All data entering or leaving the intranet, connected to the internet, must pass through the firewall. They are checked by the firewall system, and anything that does not meet the specified security criteria is blocked. Digital signatures. A digital signature consists of two pieces of information. A string of bits that is computed from the data message that is being signed along with the private key of the requester for the signature. The signature can be used to verify that the data is from a particular individual or organization. Digital certificates. A digital certificate is an attachment to a message used for verifying the sender's authenticity. Such a certificate is obtained from a certificate authority, CA, which must be a trustworthy organization. When a user wants to send a message, he or she can apply for a digital certificate from the CA. The CA issues an encrypted certificate containing the applicant's public key and other identification information. The CA makes its own key publicly available. Kerberos. Kerberos is a server of secured usernames and passwords. It provides one centralized security server for all data and resources on the network. Database access, login, authorization control, and other security measures are centralized on trusted Kerberos servers. The main function is to identify and validate a user. Secure Sockets Layer, SSL, and Secure HTTP, SHTTP. SSL is an encryption protocol developed by Netscape for transmitting private documents over the Internet. SHTTP is another protocol for transmitting data securely over the Internet. Java security. Java is used to write the web database application, then, many security measures can be implemented within Java. 3 Java components can be utilized for security purposes. The class loader, the bytecode verifier, the security manager, ActiveX security. ActiveX security model places the responsibility for the computer's safety on the user, client. Performance issues in web database applications. Web database applications are very complex, more so than standalone or traditional client-server applications. They are a hybrid of technology, vendors, programming languages, and development techniques. List of issues concerning the application's performance. Network consistency. Client and server resources. Database performance. Content delivery. State maintenance. Client-side processing. Programming language.